Today here with me is Anca Dragan. Anca is professor at UC Berkeley, where she's the director of the Interact Lab. Anca's goal is to enable robots to work with, around, and in support of people. Her focus is on algorithms for human-robot interaction, algorithms that move beyond the robot's function in isolation and generate robot behavior that coordinates well with people and is aligned with what we actually want the robot to do. She works across different applications, from assistive arms to quad rotors to autonomous cars. Anca is also co-PI of the Center of Human Compatible AI, and she's a staff research scientist at Waymo. She has won numerous Best Paper awards. She has won the Sloan Fellowship, MIT TR35, the Okawa Award, NSF Career, PKs. So happy to have you here with me. Welcome, Anca.
Thank you so much for having me, Pieter. I'm very excited to chat with you today.
I was trying to think back to maybe the first time we crossed paths. And and I'm not sure I remember it 100% correctly because it's a while ago, of course. But kind of the thing that stood with me is I saw you present, I think it was at maybe RSS, one of the top robotics conferences. And you're presenting about essentially human-robot interaction, how humans and robots can work together and achieve things together in a better way. But I would say until then, when I thought HRI, I thought, well, give the robot big eyes like a baby. It'll be more friendly, make it shorter than the person it's with, so it's not threatening. Give it a big head and all the kind of things, that are very important. But that never felt like things I'd be working on myself or anything near that, because it just felt like, pure artistry and creativity in a very different way than, mathematical works that we often do in our own work. And then there you were presenting essentially an algorithmic theory of how robots should move around humans. And all of a sudden it became a topic that I thought was really interesting for me to also try to think about. And so that's my first, I guess, memory of you.
Yeah, I'm so glad to hear you say that. I think, in a sense, I think roboticists used to have this impression of HRI. You weren't the only one. I think it was fairly common, and it was only partially accurate in that I think the community of human-robot interaction was very broad and involved people with very different interdisciplinary training. Now there was and still is a very large contingency of folks with training in either design or psychology, right? And they're investigating either how the robot should behave or look, like you were saying, right? And they were running a lot of very well thought out studies to answer these questions of, well, if I put a robot and a person together, do I want the robot to behave in this way or that way? Do I want the robot to be this? What effect does the height of the robot have on how well not just how people feel, but how well the collaboration is going? Now, there was also, I think, a contingency of folks who were doing work that was actually algorithmic in nature. So that meaning enabling robots to modify a particular motion. Speaking of motion, which was what I was doing a lot in my PhD, you could take a motion at the time. There were a lot of cool works on record something like a gesture that the robot has, and then figure out an algorithmic way to make it more expressive or to enable people to tell, that, that's the gesture that the robot is doing. And they were coming up with cool strategies like the robot should add anticipation to their motion, which is this Disney principle of animation. And they were figuring out, well, the way I could add anticipation sort of automatically on every motion that I have is, to identify a point that's sort of salient and bring it closer into the motion. And then, so if I have a wave, right, this is Andrea Tomas's work, and I know she was on the podcast with you. So yeah, so she was doing something really cool on, if I have a wave, well, what's the most salient thing? It's not as the robot is preparing to wave, it's really the see, as the hand is straight in the middle. And so their idea with Michael Gelniak was, can I identify this and then, through some heuristics, like how the hand is oriented, and then bring it closer into the motion? And you can do that automatically. So there was also work like that. I think what we've been trying to do in my lab is just maybe slightly subtly different, but it's a difference that I've been very fascinated by and cared a lot about, which is I can have someone really creative and crafty like Andrea or like Michael sit down and think really hard and come up with this notion of, what the robot can use? Anticipation. And here's how we can add anticipation algorithmically, right? So could I have the robot just figure that out? Is there a way to kind of give the robot enough of an understanding of how people work, right? And can it learn enough about how people work that if it sort of uses that, it can come up on its own with, in this case, I'll, add some anticipation. In this other case, I think if I exaggerate this way or that way, it will work well. And in this other case, this completely different strategy, like I'm sure we'll talk at some point about backing up in an intersection if you're in autonomous cars with the signal stuff, right? So can the robot just kind of come up with this stuff on its own by just knowing enough about people instead of us having to do this really hard work of designing these strategies for the robot? And sort of that's sort of what we went off with. It's been a fun time. I think I've been working at this for, gosh, how much is it? 8 years, maybe something like that, 9 years. It's really been a joy. And now there's a lot of students who graduate from my lab who are working on it. There's a lot of other folks who I've collaborated with, or, my partners in crime in the community who are working on this stuff. It's just, I'm hoping that more people like you in the robotics community have said, oh, wait a second, now this is, I actually speak this language. I don't know how to come up with the creative cool strategy, but I know how to learn models of people, and I know how to plan with them, and I know how to do all this stuff. And so it's sort of more speaking like the language that I know how to work on, and sort of helping bring them in to work on these really hard problems that, we don't know how to tackle by ourselves.
Exactly. That's what was so inspiring and intriguing to me when I saw you present. And then, of course, from there, all the amazing work you've done is that it puts the notion of essentially robots thinking about humans into play. Like most of the work, at least traditionally, is about robots thinking about objects and getting things done.
The environment, the physical world, right?
And that's hard enough.
And I will say that a big problem with all the stuff that we do in my lab is that we sort of assume that all of that works, right? Pieter will have figured this out. So starting from that, where do we go? And you're absolutely right. I think to help people kind of frame the work that I'm excited about and interested in doing, it really starts from this premise that we tend to think of the robotics problems as there's an environment, physical environment that the robot needs to interact with and change somehow. And then some clever engineer sits down and writes down some sort of goal or objective, something we'll call a reward function for the robot to optimize. It could be a reward function. It could be a constraint, like, you have to reach this goal and you cannot collide with anything. And those are the constraints you have to establish, but some sort of objective like that. And then the job of the robot is to know or learn enough about the world and figure out how everything works so that it can actually accomplish that objective. And then what we'd like to do in my lab is take that and completely break it apart by saying, okay, but now what if the robot is actually not doing this alone, but is involved in some kind of interaction with a human or with multiple humans? Although most of the stuff that we do is one human, because that's, too hard already. So how does that change the problem, right? And it changes the problem in really interesting ways, because on the one hand, you're not just acting alone as the robot now. You have a person around you as well, and they're acting in the same world. Like you're unloading the dishwasher together with a human, right? And so now okay, you have to figure out how to pick stuff up and put it places, but you also have to figure out how to move around them and how to sort of anticipate what they'll do and do the complementary thing, enable them to anticipate. You'll do a negotiation over, I kind of want to do this. What do you want to do? And so on. And so that's what I call coordination, just kind of getting your actions and the human's actions to kind of just gel well together and fit well as you're doing the task. Or maybe in autonomous driving, which is another domain that I work on a lot. You arrive at an intersection and you kind of have to, maybe you arrive at about the same time, and you kind of have to do this negotiation, this dance with the person of kind of, can I go, or are you going to cut me off, or what's going on here, right? It's not just you with the road alone. It's also this negotiation with the human. And so that's coordination. And so you kind of have to solve the problem very differently when you have this kind of crazy entity out there, the human doing stuff that you don't know about. And then the other thing that changes a lot is sort of this definition of the task, the objective, right? Which we assume kind of falls from the sky from the designer. But in a lot of these tasks, you want to think about, well, how does the person in who's in the house that I'm putting this robot in, what do they want? How do they want this robot to move? How do they want their stuff cleaned, right? Like all of this notion that I just set the objective and is to reach this goal. I mean, it's sort of like, well, the goal is in the human's head now. It's whatever they want, in the way that the robot should act should be whatever they prefer. And so at least for that, it kind of really changes the problem setting. Now you have to anticipate humans and figure out their preferences and all of that. So we think a lot about how to change these algorithms and the problem setting itself to account for this notion of humans.
So ultimately, you're putting back front and center in your work that why we're doing AI and robotics is because we wanted to work well with humans and achieve things with humans, for humans, what humans want. Now, I think for a lot of people, when they think about AI/robots and humans and how they hopefully should get along, right? There's this thing called Asimov's 3 laws of robotics, right? And so law number 1, a robot may not injure a human being or through inaction allow a human being to come to harm. Law number 2, a robot must obey the orders given it by human beings, except where such orders would conflict with the first law. And then law of number 3, a robot must protect its own existence as long as such protection does not conflict with the first or second laws. And so how about those laws? I mean, can we just give a robot those 3 laws and just say, hey, here are the laws, and will that work?
So a few comments on that. Maybe the most obvious one is that, let's say you do this, they tell a lot about how to be safe around humans, but this notion of should I bring Pieter coffee in the morning and wake him up or not, or whatever, all of that is still in Pieter's head and it has nothing to do with these laws. So you kind of still have to do that hard work, right? So that's one aspect. Now, the intriguing thing, I think, for a lot of people is, can I implement these laws and will they hold, and will the robot not hurt me as a consequence? Will the robot do what I want, at least from the perspective of not doing anything catastrophic? Can the robot still revolt against me and following those laws? That's sort of the typical. And I think the challenge with Asimov's laws is you can kind of find in Asimov's writings, because if I'm not mistaken, most of the stuff starts with, okay, here are the laws, and then here's the kind of edge case that you encounter in the world where it turns out that you don't want to follow those laws. And actually, there's some loophole in them. There's some weird thing happening where if you interpret them literally, all hell breaks loose, right? So I think the challenge is both in taking these English words and turning them into code or math that actually sets an objective for a robot, or a constraint for a robot, as well as, even if you did that well, those three laws themselves might not be complete. In other words, there might be a lot of exceptions to them, right? They might be like, okay, this is what I want you to do in general, but here's some weird situation where actually I kind of prefer something different. Stuart Russell, who we both work with a lot, has this great example like this of King Midas, right? So King Midas, I don't actually know much about King Midas. I heard this from Stuart many times, so I can tell it. So King Midas was a king, as the name suggests, and he wished that everything he touched would turn into gold. So you can think of this as, an English specification of an objective, and it sounds great. And so we can say, well, can people just tell us what they want? And then we'll get the robot to do that. And so imagine you had this robot that said, yes, I'm so glad you, my end user, tell me what you want, and then made it happen. Right? This is essentially what happened, except without robots. And then it turns out that that's not quite what he meant. Like, he did not want that his food that he touched would turn to gold, and he did not want that the people that he touched would turn into gold. So there's always, we can write these generic things in English, and there's always a ton of different edge cases and exceptions to these. And I think that's where the problem lies, is all of that is implicitly in our heads as the end users and even as the designers of these systems. How do we go about enabling robots to sort of help us express these things that are in our head, despite our inability to actually write them down or say them in words in enough detail with enough nuance that it will lead to them incentivizing the right behavior for the robot at all times.
I love that example you just gave. And Anca, I love the way Forbes described you touching upon this. So Forbes wrote, "Meet the woman who is teaching machines to second guess us." And it sounds like exactly what you're describing now too.
Oh, yes. Absolutely. It's the idea that when we write something down, where we say something to the robot, it's not the definition of what the robot's objective actually is. That this is a complete falsehood that we've been living in an AI for many years now. And that is not just, I think we know this about end users, that when they say something, you can't just take it literally. But we certainly, I think, have been falsely assuming that when one of us sits down, or one of the experts in AI sits down and actually can write code, so you surpass the English translation to code, you actually write the code directly, then somehow magically, that's the definition of the objective, and you never get it wrong, and that's what happens. And I think a lot of what we've been working on with Stuart, has been this idea that even when this expert writes down in code something, it's really just their best guess so far at what this objective for the robot should be. And we see this with, you don't have to get to very complex notions like human values and so on, which are clearly very hard to write down in code. But even simple things like you take a car, you want it to trade off between, like it needs to get to where it's going. It needs to not hit stuff. Though both those things are very important. And it needs to follow traffic rules. And traffic rules include things like you shall not cross double yellow lines. Mm-hmm. But clearly, if you're about to get into an accident, you will cross double yellow lines, right? And maybe even for, I don't know, how much progress do you think it should spare the passenger of the car for it to be okay for the car to cross a double yellow line? Is it 5 minutes? Would you do it for 5 minutes? Would you be okay with the autonomous car technically breaking the law to kind of move everyone forward and then maybe not just the passenger, but everyone around, and unstuck a bunch of traffic, as opposed to like be stuck there waiting and waiting and waiting? because the thing in front of it is out in San Francisco all the time, right? There's stuff parked. You have to go around it. You'll cross the double yellow line. Do you want the car to just be stuck there behind? Probably no one wants that. Not even the lawmakers who wrote the law about the double yellow lines want that, right? So what's tricky is you write something down and it's sort of your best guess at how these things trade off. You're going to look at a bunch of different situations and make sure that the behavior makes sense. And then you're going to, put the car out there in the world, and hopefully those trade-offs that you specified make sense. But usually there's always some edge case where, oh gosh, now because I made it okay for you to cross double yellow lines here, you thought it's okay in this new situation to cross double yellow lines, but there was someone else coming from this and that. Is there some complex thing that you haven't really thought about as the engineer? And then the car does the wrong thing. So what we've been saying has been, look, this specification of the objective is really, you have to second guess it as the robot because it's not perfect. People are not magic. Even engineers are not magic oracles that get everything 100% correct. And really, it's going to be this iterative process of writing stuff down, seeing what happens, revising it. And so we might as well tell robots that that's what's up, right? As opposed to telling robots, this is the objective, you have to do this, right? And so now the robot has to look at this and say, okay, well, what's the context in which you specified this? What are sort of the situations that you even looked at? Well, I can sort of trust that this makes sense for those situations, but maybe I shouldn't trust that it makes sense everywhere. And maybe I can actually help you, Pieter, to write down this reward function, this cost function objective better. Maybe I can sort of search for different hypothetical situations that I'll be in, and just double check with you. Hey, like if this happens, do you really want me to, optimize for this, or is that okay? Or should I do something else? Like, let me tell you my holy grail. The holy grail here is I'm going to come up with this very exaggerated, silly example, but let's say that I make a navigation robot and it's largely for, the Berkeley area and so on. So I think about Berkeley and I think about, well, it has to know about how to deal with grass and, there's sometimes some dirt roads on campus and so on. And so I write down, an objective that's sort of telling it what's good and what's bad in here. Grass, don't go on it. That would be kind of bad, but it's okay if you have to in order to avoid someone, blah, blah, blah. Okay. So let's say I did all that. And now the robot goes to Hawaii and there's a lava eruption, right? I haven't told the robot that going through lava is probably a bad idea. I told you this example is very silly, but here's the holy grail. The holy grail is that I write down my objective and the robot thinks about it and says, here's a hypothetical situation where I encounter, water or lava or whatever. What you told me to optimize for would send me right through it. Are you sure, Pieter, that that's what you want me to do? And then you, Pieter, can go and say, oh, no, that is not what I want, and sort of be able to revise things. So that's sort of the holy grail. Can I enable the robot not only to not just blindly optimize for what you said, because it's clearly going to be incomplete, but help you? Right? Work with you the way we work with end users when we think about, helping them understanding what they want. I think that the same thing should happen with experts as well. Can robots kind of give us a hand at figuring out what we should be writing down, specifying for them to do in the first place?
That actually reminds me a little bit, and it's a bit different, but it reminds me a little bit of when I was talking with Andre Karpathy on Tesla's self-driving car project, right? Where the system was set up to understand when it doesn't recognize certain things well and to automatically collect more data. There, it was getting more data of a type that it didn't have enough data of automatically, right? Let's say stop signs, if they are not detected 100% or sufficiently accurately yet, bring in more stop sign data automatically. And in your case here, okay, it seems you're essentially saying it's not necessarily going to be more data bring in, but the robot or the car or whatever is the autonomous system is also going to be aware of its current limitations, or we want to equip it. I mean, it's hard to do, but we want to equip it with some awareness of its limitations, and then actually circle back to the engineer that built it and just say, hey, actually, you never designed me for this situation. I can do what you programmed me to do, but you never thought of this situation. So I might completely fail in this situation because you didn't anticipate it.
This notion, there's a more general version of this that has nothing to do with objectives. That really comes in supervised learning, right? So a lot of the way AI systems are trained, the sort of the most basic way, I'm sure you've talked about supervised learning on this podcast before, but just kind of to recap, get a bunch of data, input to output, right? And you train a model that can, given you input, predict that output. And I think what we're seeing in the era of these models being very high capacity, so giant deep neural networks, is that they have this magical ability to take very raw data, so a lot of information as the input, right? Pixels, stuff like that, and then construct the features that then are useful in explaining the data and coming up with that output. And what we're seeing, maybe even that was a problem in machine learning before, but even more so these days, is because of these high capacity models, is that sometimes it's easy for them to converge on what we might call the causal explanation for the data, but other times they'll just pick up on spurious correlations in the data, right? These patterns that happen to be there. I think Sergey Levin had this glorious example in driving of training an autonomous driving policy, and he was doing it from dash cam images. And what was happening was that you can learn very well when someone will brake or is braking. You can predict that brake decision by looking at the dashboard and seeing the brake light come on. So if you just do that by supervised learning, you'll notice this amazing correlation in the data. It's amazing, very helpful pattern that helps you figure out that you should say brake, because every time there's a brake light on, bam, you brake. And so that's a big problem because, in the real world, you brake because there's a pedestrian you're trying to avoid, not, and then as a consequence of you braking, the brake light comes on, right? So this is kind of the messed up causality. And I think the issue that we're seeing in all models, be it when we do supervised learning or when we learn rewards or whatever, is that there's always going to be a lot of different explanation, different models that fit the data. And if you're not careful, you're going to converge on one of them and it might be the wrong one. It might be the one with the patterns that are spurious correlations, not the causal one. And that will especially be true if those spurious correlations are much easier to construct. Like looking at the brake lights is much easier than, identifying the need to brake because there's a pedestrian or because there's a stoplight. And so that's much more complex. And so I think the whole community is starting to think about this notion of, can we somehow detect that we're seeing an input where that's out of this out of distribution, right? That's different, where correlations that we've seen no longer hold. Can we kind of detect that? and then try to do that actively, where we say, can we hypothesize such an input that we might see, and then make sure we collect data there. And so what I'd be very excited to see happening, we started doing this a little bit, and I can't really say that we're fully there yet, but that's the holy grail, is doing this for the reward function specification itself, right? Just kind of looking at the reward function, the objective, and saying, I think it makes sense for these contexts because you verified it and clearly you thought about that. But are there these outlier contexts, these edge case situations where I'm not going to be, I don't know. And so instead of just coming up with one explanation for what you want based on everything that you've looked at, I should sort of think about all the hypotheses and try to come up with new situations that help disambiguate between them, that I can expose you to, and you can give me some feedback, whether it's you revise your code or whether it's say, no, don't do this. All of those are useful signals for the robot for the robot to then use to learn more about what you want. So I think there's just these two recipes here. One is have uncertainty. So don't just go with one explanation that makes sense, but kind of try to keep track of all explanations that make sense. And then try to come up with new inputs that disambiguate. It's very easy as a concept, right? But it's easy in theory, but it's difficult in practice. And so I think as a community, we all have to work to try to get there.
But I really like this, the way you described it, because essentially, if I were to reframe it, I would think of it as, okay, instead of having a robot be tasked to do some task that you say, this is your task. Instead, the robot, at least the way I'm interpreting it, is going to second guess what we ask it to do. It's going to say, if I'm asked X, there's a whole range of things I could actually be asked when somebody says X. And, if all those things make me do the same thing right now, I can just go ahead and do it. But if there's actually a difference, I can go back to either the person who asked me, or maybe call back to the engineer if it's a more kind of, engineering thing that I need resolution on, and resolve these things. And so it's like your robot's getting into a conversation with you all of a sudden. You might say, hey, can you unload the dishwasher? And it might actually, get back to you and maybe say, hey, are you sure it hasn't run yet? Do you maybe want me to first run it?
That's the dream. That's the dream. But let me see. I think the key here is that whatever you say, and even if it's very specific, if it's a sequence of instructions, right? So your example is the high level task, unload the dishwasher. But if you just provide a very specific sort of sequence of steps, right? Then that maps to a behavior for the robot. And part of our observation was that you should be looking at that behavior in that context, and then be able to say what other sort of high level specific, what are things you could have said that would actually lead to that same behavior. And now I have this whole repertoire of possible kind of candidates for what you might want that all map to exactly the same thing in this particular situation. But if I want to apply them to a new situation tomorrow, right, I have to be very careful because you haven't thought exactly about what new type of, setup we'll encounter tomorrow. So I think it's like kind of being cautious to not just transfer one specification everywhere, but sort of looking at, well, what does it mean for this one context? And then can I think about all the other things that you could have said that would have led to the same behavior in that context?
I like this notion, everything you could have said. So it's like you tell the robot something, and then the robot's just thinking, okay, what could she have said instead? And it reminds me of, we had recently a conversation with Alison Gopnik, who, of course, very well, one of our colleagues at Berkeley. And it turns out she invented the notion / phrasing theory of mind, the notion that people can think about what other people are thinking. And you're essentially saying you're trying to build algorithms. Can you say a bit more about that? How do you even get started? How do you, ultimately you need to program a robot, right? So how do you go to your robot and program it to have a theory of mind
of humans? Yeah. So that's exactly right. That's a lot of times that is how we talk about the work of giving, endowing robots, right, with this understanding of human behavior, which is essentially giving them a theory of mind of people. And that means the decisions that people will make, the beliefs that they have, and so on, right? All the stuff that happens internally to a person. And maybe before we talk about how we do that, let me say a few words about why that's useful, right? So, and it's useful in two ways. One sort of main way is if I can have this understanding, this model that links humans' internal state, their beliefs, their preferences, that I can't directly observe, right? They're in their head. But if I can have a model that links that to the stuff that I can observe as the robot, which is roughly the actions that they take, how they move, what they say, all of that, then I have a chance at observing the stuff I observe, the actions, and kind of tracing back what could possibly be in their head, right? So if we talk about robots that understand human preferences, then and human values and so on, then I think, unfortunately, because we can't observe those directly, we can only observe what people say and do. Theory of mind is kind of this way to obtain that link and be able to infer the stuff you can't see from what you can. And so that's one main way that we use theory of mind. And then the other way is for this coordination problem, for prediction, right? So you can, if you need to anticipate how a human will move, how a human will do something, how a driver will drive, how a pedestrian will move, how the person whose dishwasher you're emptying will kind of come and try to help. If you need to make those sorts of predictions about human behavior, then you could just collect a lot of data of human behavior and sort of say, okay, I've seen a state like this before. What has the human done then? I can predict that they'll do something similar. So this would be the sort of the supervised learning approach, right? You collect a lot of data, input, output, everything's input, output, and you just have models of people that way. And that completely bypasses the need to look at anything internal, right? Are they making these decisions based on anything that they care about or they believe in? Who cares? It's just input, output. And that is a glorious approach, and it works very well in some cases. But the issues where it struggles goes back to exactly what we were talking about earlier on correlation versus causation, right? It's easy for these models to pick up on sort of silly patterns that help them explain human behavior without actually being causal. And the challenge with that is that in a new situation now, you're not going to generalize. You're not going to know how, you're going to make the wrong prediction. And if you make the wrong prediction in driving, that can lead to a crash. If you make the wrong prediction in someone's house, that can lead to you bumping into them or you sort of, getting in their way. And those things are bad in robotics. So we don't want them. And so one way we've been thinking about theory of mind helping there is by structuring the space. I'd say by giving the robot some sort of inductive bias about human behavior, but it's really structuring the space of possible behaviors. Many arbitrary things that no one will ever do. And so the question is, how do I kind of tell the robot this is not what a real human would ever do versus this is something that's actually plausible? And I think the more you understand about, the reason people behave in the way they do is because they have goals, they have intentions, they have beliefs about what's there and what's not there. And all of that informs the actions that they take. The more you can kind of help the robot by informing it about that structure, the more, the easier time it can have to actually make sense of the behavior in the correct way. And so that's roughly how we use theory of mind, right? To get robots to make better predictions about human behavior, but also to get robots to actually understand what's in the person's head, which we really don't have another way to do other than by linking what's in their head with the stuff that the robot can observe. So, yeah. So you're asking how we give robots a theory of mind. How do we? Yeah. And when I started doing this kind of work, I'll say that I just cheated and made the robot think that humans work the way robots work. That's roughly the recipe. And that took us, quite far, actually, surprisingly far. So how the robots work, robots have internal states, quote unquote, right? They have an objective, they have estimates about the world and so on. They have beliefs. And And so if you want to know how a human will act based on the objective, just kind of pretend like they do what robots do, which is they do optimization, right? They come up with the optimal thing to do for that goal that they're trying to attain. So you want to know how a driver will drive to their destination? Just kind of pretend that they're an autonomous car. What would they do? They would optimize for the best way to reach their destination. Okay, cool. So that's a model of human behavior, right? That links their destination to the actions that they take. It's not a particularly great model because people aren't robots. We don't work this way. But it's a starting point. It sort of says that instead of human actions being completely arbitrary and impossible to predict, people will make some sense. They'll do things based on the intentions that they have, things that are optimal in this case. This is the same as the economists were doing 5 decades ago, right? There was this notion of utility, and people are utilitarian, and they'll take actions that maximize their utility. And that was the model that they used for human behavior. Now, and conversely, if you talk about, well, how do people form estimates of the world? How do they, have beliefs and look at new information and make sense of that information and update their beliefs? Like, what's going on in people's head? Well, you know what robots do? They do Bayes' rule. Bayes' rule is this magical thing that says, if I can, observe this, but I'm trying to estimate this, my estimate of that second thing, right? I can just come up with that based on knowing, okay, well, if let's take a concrete example here that will help. If I'm a robot and I don't know whether Pieter is going to the bathroom or to the kitchen, I want to estimate that, right? And I can't observe this. But if I see Pieter start taking a step, I can look at that step and sort of say, okay, does this step make sense if you're going towards the kitchen, right? Is in the direction of the kitchen. Does this step make sense if you're in the direction of this other goal? And that's Bayes' rule, right? That's what robots do. They say, is this evidence consistent with this sort of hypothesis? If yes, then the hypothesis has high probability. Cool. So that's how robots make estimates. And so we thought, well, it's like a pretty decent way to make estimates. Maybe that's what people do too. It turns out there is actually some cognitive science work, for instance, coming out of Josh Tenenbaum and Chris Baker, that have not confirmed by any means. We don't know anything about how people actually work, but that sort of have given quite a bit of credence to this notion that people might actually be running Bayes' rule implicitly in their head. Anyway, so that's how we started with theory of mind. Bayes' rule and argmax. You optimize for your objective, and it's just what a robot would do. Okay. And then this works sometimes, but of course, if you watch human behavior, it does not look at all
not very rational. Yeah.
Not very rational, not the optimal thing to do. And so what can you do? Well, you can add a little bit of noise and say, well, it's not perfectly rational. It's rational plus some noise. There might be some errors, but of course, that's also not how people work. We have these systematic biases, systematic deviations from optimality. And behavioral economics has been a field that has looked in depth at this. So they've characterized an ever-growing list of human biases, human cognitive biases, describe that in sort of various degree of formalism. So some of it is like, we actually have a formula that explains this. And for some of it, it's just, we observe this in some studies. But to give you some examples of what people have found, there's optimism or pessimism bias. So that is sort of we can't deal with probabilities. This is my cat triggered. So we as humans cannot deal with probabilities very well. Let me say that again. We as humans cannot deal with probabilities very well. So sometimes we kind of tend to assume that the best thing will happen, the thing that works out for us. Sometimes we tend to be very pessimistic and assume that the worst thing will happen. Sometimes we amplify the probability of those worst things. I do that all the time. I'm a very high anxiety person. So I always take the worst case. And in my mind, it's, 10 times more likely to happen than it actually is. So those are some examples. Our sort of utility that we derive out of something tends to plateau. So, if you ask me how much I care about getting $5 versus $1,000, I'll be like, oh my God, $1,000 is so much better. But if you ask me, do you want, 1 billion or 5 billion? This will be a much sort of smaller difference in my head because these numbers are so large. I can't imagine having $1 billion. So these numbers, I'm just a Berkeley professor. So these numbers are so large that it just, whereas, if you're a utilitarian, if you're perfectly rational, right, these differences are huge. So those are some examples of human cognitive biases. You go to the supermarket and you get tempted by the cookie at the checkout aisle, even though you're on a diet, right? It's not the rational thing to do, but you do it anyway. And these are not very well explained by adding some noise, taking rationality and saying that there's a little bit of errors that people make from time to time. And so one challenging thing lately has been that we started to encounter these tasks where just assuming that people are noisy rational is no longer cutting it. Right? There's this famous quote, all models are wrong, but some are useful. Assuming that people act like robots has been somewhat useful, surprisingly so, even though it's wrong, for many different tasks. It's a reasonable enough predictor of human behavior that when you give robots that, they have kind of figured out things to do with people. But we've also started encountering situations where it doesn't work anymore, where maybe the suboptimality is so high that you just can't make sense of that behavior. And so one example is this is a kind of very silly one, but it's inspired by some experiences we have when we try to get people to operate robot arms. So when you give people some interface like a joystick or something like that, and you ask them, hey, control this arm to get it to move into the right position. And we do this in the context of assisting people with motor impairments, right? They're in a wheelchair. You kind of want to put an arm on their wheelchair and have it work as an extension of their body. We also, and I'll talk about this a little bit later, but we have this awesome collaboration with a neurologist at UC who's implanted this brain machine interface, this ECOG array into a patient's motor cortex. And he tries to operate an arm with his thoughts, which is amazing. So we've noticed that when you do stuff like that, people have a really hard time, right? And it's not, you can try to infer what they want and try to, by assuming that they're operating the robot in the optimal way, but it's just so far off from optimal that you cannot figure out what's going on. And usually it's not that you can't figure it out, so you're confused. That would be still okay. It's that you become really convinced that, they want to pick this up. This is clearly what's going on because, none of the explanations really make sense, but this is by far the one that makes the most sense. And so the robot ends up with this being very confident that you want to pick up, your bottle when in fact you want to scratch your head or something like that. And then it starts really assisting you with that and kind of gets in your way and is really frustrating.
We are dropping new interviews every week, so subscribe to The Robot Brains on whichever platform you listen to your podcasts. We've known each other for many years now as colleagues at Berkeley, and even while you're at Carnegie Mellon doing your PhD, we knew each other because we meet at the conferences and so forth. But, you know, there was Anca before doing PhD in robotics at CMU. And I'm kind of really curious about that. You know, young Anca, you know, what got her intrigued about all this? What got you started?
Luck and a series of coincidences. Yeah. So I was born in Romania, and I lived there throughout high school. And I think that was a very lucky break, because Romania is a country where, if you look at, say, the number of degrees awarded in STEM, 55% go to women. This is an old status from 10 years ago, and that's compared to 20 something in Germany and 30 something in the US. These are older numbers, but you know, when I was looking into this a few years back, that's what I found. And I don't know why that is, but I think one part that contributes to this is that where, you know, it's a post-communism environment where it's not shameful to be good at math. It's kind of shameful to be bad at math. You get made fun of if you're bad at math, or at least it used to be the case when I was growing up, and it was just it was not acceptable. Like, you could it was just something that everyone had to do, regardless of gender. And I think that was kind of very lucky for me growing up in that, because I didn't have a chance to say, oh, you know, look at my mom and my aunt, you know, they have these type of careers. They're not the engineers like my dad and so on. So ergo, I'll probably be more like this. And that was never an option. My mom is an engineer. She's a chemical engineer. But that was never an option. And somehow I just went into it, and I never questioned whether I'll be good at it or not. I just kind of knew that I had to be good at it. And so I think that was, in a sense, the start of, I went to the Math Olympiad and so on. I got very interested in that. And I also got interested in computer science, which luckily I got a chance to start, not computer science, but programming. I started in the 4th grade. Oh, wow. My mom has a story about this. So there were some extracurricular activities you could sign up for. And, you know, she thought I'd sign up for dance or something, like some reasonable thing that a 4th grader will want to do. And it's like, programming in Q Basic, that sounds fun. I want to do that. We started going and learning about programming. And then my school actually ended up having it all the way in middle school and through high school, programming and then algorithms. And there was an Olympiad for that too. And so I found that really exciting, because on the algorithmic side, it felt like it was combining the math part with doing something tangible. And it was that combination that I think felt really cool. And then in 12th grade, I illegally downloaded Stuart Russell and Pieter Norvik's book, Intro to AI. Yes. And
Stuart, 100.
I owe Stuart money for it. But I rewrote the robotics chapter last year for the last edition. And so I think that I paid back my dues doing that. I found Stuart's book, and there was something so cool about this notion of, I was reading about search, which is this very basic type of AI, right? You don't really call it AI anymore, because we know so much about it that it's sort of, now it's search, it's not AI, right? Every time something is figured out enough, it's no longer AI. Only the stuff we don't really know how to do, that's the thing that we call AI. So search was in this book, and at the kind of towards the beginning, and there was in search, you're just saying, okay, I'm in some sort of starting state. I need to get to a goal state, and there's actions that I can take, and combinations of actions. Some combinations will take me to the goal, and I have to find one such combination, ideally one such combination that's the most efficient. And this notion of, I give a computer a task like a goal, and I say, figure out how to get there. And it, does some computation, and it just figures out how to do that, which just blew my mind. And I really wanted to work on stuff like that. And so when I went to college, I knocked on my AI professor's door, and I said, okay, well, I'm just a freshman. I don't know anything, but what would it take, to sort of get involved with this? And that's kind of how it got started.
And did he tell you should go do an internship at Carnegie Mellon? Is that how you ended up there? Or
I did my undergrad in Germany at a college called Jacobs University. And they had this relationship with Carnegie Mellon that was an exchange program. And so every year they would send 2 people to do a semester at Carnegie Mellon. And I got to be one of those 2 people in the year that I went up for it. And so I got to go there, and I got to do research with someone at Carnegie Mellon. And then I was taking Ilan Nurbash's Intro to AI class. And I told him, hey, I'm applying to PhD programs. I'd like to continue doing research in this. And he said, you should apply to the Robotics Institute. Because I wasn't into robotics. I mean, I was into AI sort of broadly, but I didn't really, know what kind of AI. And so Ela said, you have to apply to the Robotics Institute as well. And then I thought, I like optimization. I like these sort of techniques. That's what I do. And applying it to the robotics type of domains seems really intriguing. So I applied there, and that's where I ended up going for my PhD. And I was just doing motion planning, but then in Srinivas's lab, and then I got into humans through, I can't even tell you. So basically I was part of this quality of life technology center, and it was supposed to be about assisting people, older adults, to live more independently. And we weren't working with any people that we were trying to assist to live more independently. We were working on picking up the bottle and moving it there. And so then I asked the question, should our way of picking up the bottle be different? Should our algorithms that tell the robot how to pick up the bottle, should they be different if there's someone watching? And that led to my thesis on, well, let's maybe move in an intent expressive way so that people realize what the robot is going to do. And to that point, the way we did that was pretend that people do Bayes' rule on what the robot is trying to do, and then have the robot move in such a way that when people do Bayes' rule, they end up on the kind of correct hypothesis, correct explanation. So that was the start of it.
Now from there, of course, we were so lucky to hire you at Berkeley and get you as one of our colleagues. You had so many options, and we were very lucky you chose Berkeley. What was interesting to me is you showed up, and of course you kind of started thinking even more broadly about how robots and AIs and humans can interact. During a PhD, it was a lot for manipulation robots. But then it was very interesting. You were just recently arrived at Berkeley, and you joined as an additional job on top of your Berkeley job, you joined Waymo. And now I would say when a lot of people, including me, definitely at the time, think about self-driving cars, and would think about, okay, does it really see the stop sign, or does it not see the stop sign? I need a better vision system. Or does it see the car pedestrian in front? And then, of course, it needs to hit the brakes in a reasonable way and not start skidding. And so there's challenges there. You don't want to brake too hard. And so there's a combination of kind of vision and control challenges. And then you went to Waymo. And as I understand it, you effectively started taking on a whole other suite of problems that was largely ignored. Can you say a bit more about that? Like, what if a car can perfectly see what's in front of it, and it can perfectly control its path. What are the remaining challenges?
Yeah, so cars are pretty good these days at doing those two things, and they're not everywhere, right? And so it's very natural to ask, well, what's missing? And a way that I'd like to answer this is take a busy city like San Francisco, and now remove all the people. Remove the pedestrians, remove the motorcyclists and the bicyclists, and now remove also all the vehicles that are driven by humans. Is there still a big problem left to solve? And the answer is not really. We could navigate in any city that has those properties.
Empty cities, no problem.
Empty cities, no problem, right? Because vision, control, all of that. It's just planning. We can do those things. Maybe not a bunch of years ago, but these days, those technologies are really reliable. So the problem is, how do you get the car to still do the things you want, get there and so on, but do it in a way that meshes well with the existence of these other agents, these humans that are all around doing things. And so that kind of fell into my wheelhouse of, well, how do you get robots to generate their behavior when they're not acting in isolation, but they're actually acting around people? And so the challenges there end up looking like, if I want my car to navigate well, I need to be able to not just detect where humans currently are, but it needs to prepare, right? It needs to anticipate certain things. And so it needs to know where humans will be in the future. How far in the future is the kind of still an open question, but enough in the future that you can sort of figure out what you're supposed to be doing as the autonomous car. And that prediction is exactly, the sort of thing that we were talking about earlier. It's anticipating the decisions that people will make. And you can collect a lot of data and sort of treat people as black boxes. And then you kind of worry about the robustness of that. And so then you kind of maybe want to think about marrying that with approaches that are more based on, theory of mind assumptions about people. And then yet don't constrain the problem too much with that, right? You don't want to say, well, people work as optimizing for their goal, because they don't, and then you'll make the wrong predictions again. And so figuring out sort of how to navigate the space of what will humans do, that's one problem. And then it gets more interesting, because imagine that you're trying to merge on a busy highway. And so you have a bunch of people coming. The prediction problem for what will they do is very easy. They will, they're going at 60 miles an hour. They'll keep going at 60 miles an hour. That is the most likely thing that they'll do. And so now your car, armed with that information, will decide that it has to wait until there's a big enough gap in traffic that it can fit in. But unfortunately, that means that you either sort of stop and wait for a while and then piss off a lot of people behind you, or you keep going, hoping that there'll be a gap at some point, and then you sort of miss the margin, take the exit. And so both of those options are really bad for an autonomous car. And somehow, not that this never happens to people, but this very rarely happens to people. Somehow, when faced with this dilemma of which of these two bad options do I take, people invent a third option, which is they just kind of nudge themselves in there. Why? Because the person behind starts braking and they create that gap in traffic right? And so what's going on there? Well, that's more than just a prediction in isolation. That's now about how what the human decides to do depends on the decisions that the robot, the autonomous car, is making. And that kind of back and forth between these these autonomous car decisions and human decisions, that's what I call coordination. So how do you coordinate properly with people? Not just anticipate what they'll do, but anticipate what they'll do in reaction to you. Mm-hmm. And then it gets even more complicated because people also know that, so they not just respond to what the robot is doing, but they know that the robot is responding to what they're doing. So, I used to drive a lot, not in the pandemic, but I'd go on the Bay Bridge to commute back to San Francisco from Berkeley. And it's always crowded on the Bay Bridge. And then there's always some poor person trying to take, make a lane change or do a merge or whatever. And if I'm in a good mood, I'll slow down like a good citizen and let the poor person in. But if I just, had a conversation with Chris and we argued about something and I'm pissed, I might actually be like, no, you have to wait, and I'll accelerate and then get the person to back. So they started going and I'll accelerate, and then I know that they'll back off, because what are they going to do, right? Are they going to really go in and collide with me? No, right? So it's hard because not only will people respond to what the robot is doing, but we have to be careful because they'll also try to influence what the robot is doing. They know that the robot responds to them. And so, and the work that we do at Berkeley on this, we've figured that the best way to make sense of all of this mess is via something called game theory. Game theory is the tool that kind of enables us to say, we have two agents and they each want to do their own thing. In this case, I want to drive and make progress. You want to drive and make progress. We both want to not collide with each other. So we each have our own thing that we're trying to go for, but we're, acting in a way where my actions influence what state you'll be put in, and vice versa. And so that's how we've been wrapping our heads around this problem: is how do I go about solving this, what is called a general sum game. And then what gets much more complicated is you can try to solve that. It's very complicated computationally, but you can approximate it in various ways. But then you run into the problem that people are not perfect little game solvers. So you come up with these beautiful solutions of, here's how this game is going to work. You're going to go in, the person's going to do this thing. If the person accelerates, you have a way of backing out. If the person doesn't accelerate and brakes, then you can go in. So you can kind of come up with these sort of complicated policies for both the person and the robot. The problem is that people are not game solvers. They're not going to take their utility and do the rational thing with respect to their utility. And so you have, again, this issue of trying to, if you want to do this realistically, you have to marry that with data of how people work and have to account for these, potentially systematic biases, systematic deviations from rationality that people have.
That's so interesting. Now, have you actually gone to Phoenix where the Waymo cars are driving? And have you experienced some of the cars having some of that theory of mind behavior yet?
So first of all, I cannot say anything about whether Waymo cars have a theory of mind behavior or not, because that's confidential. But I can, tell you about the stuff that we do at Berkeley that's related to this problem. But so have I gone to Phoenix? I have not gone to Phoenix. I was about to go to Phoenix, and then the pandemic happened. So I have not made it out there yet. I have seen many videos from Phoenix, and it's always very, very cool to just look at the car without any driver and, passenger in the back, usually taking a video or something, and or just minding their business and looking outside, and just kind of see this car take good decisions, usually one after another. It's amazing. Now I did get to ride a lot in cars around the Bay Area, and actually way before I joined Berkeley, before I joined Waymo, when I was in Berkeley for RSS. So Pieter, you organized this big robotics conference. This was, I think, maybe 2013, 2014, something like that. And so I came in for RSS, and part of the program was we went to Mountain View to the Google campus, and Waymo has been just a Google chauffeur, Google self-driving project, and they gave us rides. And as a sort of a new roboticist, dealing with how it's impossible to get an arm to reliably pick up a fuse bottle. That was my life then. Getting in this car and then just taking this ride where it consistently takes one decision after the other. Kind of this was in a sense, the realization of this thing that when I was in 12th grade and I was reading Stuart's book, I was like, what's cool when you give a robot a goal and it figures out decision after decision to take in order to actually get it there. And it was that, on steroids with all the complexities of the real world, as opposed to just abstracted away in a graph, happening live, and I was in it. I was riding in it. And it was just kind of, I don't know, it was in a way a life-changing moment. It gave me such an appreciation of this type of work. And I think it got me sold on not just looking at manipulation, but looking at driving and navigation as well, as part of the work that we do. Something
a lot of people, of course, wonder about as more and more robots come into the world, maybe more self-driving cars, other robots. The common headline that, journalists like to use, I guess, and people, like to click on, that's kind of a feedback loop there, is robots could come in and AI could take over the world. And I think of all people, you've actually thought about this quite a bit. What do you think? How realistic? And if it were to happen, how would it happen?
Yeah, I think what comes to mind is that the media likes to portray it as the Terminator somehow, that the media tends to say something like, there's going to be this robot uprising. But I mean, if you look at Westworld, for instance, right, there's this, at some point, the robots decide that's it, they've had enough, and they decide to kind of take over the world, right? And this is, in a way, highly incompatible with the current way AI systems work. Now, that's not to say that AI systems will always work the way that they do now, but, in terms of, if we think about what we were talking about earlier, the basic setup of you have some objective, loss function, whatever, and then what the robot does is it tries very hard to really nail that. It's like, this is my life. This is what I live for, is this brownie points that this reward function gives me. So I'm trying really hard to get as many brownie points as possible. And that's its whole universe. And so what's incompatible is this notion of, somehow the robot is going to decide to adopt a new objective that makes it do something else, because that would lead to behavior that's suboptimal under the current objective. It wouldn't get the brownie points anymore. And it really wants to get that. So that's all its job, right? So I think that sort of scenario seems very far-fetched, but I think the stuff that could happen is that the way we set up the brownie points is wrong, either purposefully, right? Or I think, and the stuff that we worry about in the Center of Human Compatible AI is also just accidentally, right? That, and I don't think we have to wait for the much more sophisticated AI and the robot uprising. I think if you look, for instance, at recommendation systems today, what a lot of what has probably gone wrong with them is that the brownie points, what they're incentivized to go for is, to a largest extent, will you, the user, click on this thing or spend time watching it, right? And so that leads to this kind of weird incentive for the system, for the AI agent, to show you a lot of things you're likely to click on. But those things, if you think about what people are likely to click and spend time on, it's not what makes them happy necessarily, right? It's a lot of, the more kind of scandalous it is, the more kind of tempting it will be, like the cookie in the supermarket. The more sort of polarizing it is, the more sort of extreme it is, right? The more kind of, again, it will be more engaging. And so you'll spend more time on it. And I think that's kind of not necessarily the companies maliciously, not optimizing for user happiness. I think even if companies really tried very hard to optimize for user happiness, it'd be really difficult to tell what that is. Whereas, will the person click on this? If yes, you get a brownie point. If not, no, is a much easier way to set up a system. And so I think this is a challenge that we face, and we don't have to wait until, the sci-fi like stories. I think it's affecting us already that we set up these systems with the wrong objectives, with the wrong loss functions, and then their behavior has unintended consequences. It's not necessarily about anyone being malicious. It's really just unintentionally causing problems because you've sort of set the system in motion with the wrong objective, and it's trying to do such a good job at optimizing for that objective you told it to.
I mean, another way to phrase it would be that these recommender systems are like great. They're great optimizers at their brownie points system, except we give them the wrong brownie points, which is, how much time people spend online or click on things. Now, it also seems really hard to give the right brownie points because, and so I'm kind of curious, are you optimistic that this can be figured out, a way to even, let's say, just in the context of recommender systems, is there a way to figure this out, or what's going to have to happen?
Yeah, I'm cautiously optimistic. I think it's a really, really difficult problem, and we certainly don't have great solutions for it. But I can talk about a couple things that I think are helpful. One of the things that's really, really helpful is this notion that when we give the system an objective, it shouldn't trust that is the objective set in stone that we wanted to actually optimize, because we might be wrong. Mm-hmm. I think with click-through rates, I think we're wrong, for instance. So one thing that helps a lot is if you can, as the system, you can maintain some level of uncertainty over, well, what is the right thing? What do you actually want me to optimize for? And come up with, different possible hypotheses for what the right thing might be. And even if you can't get any more information about that, you can at least be conservative. So you can do things that sort of hedge bets among different aspects. And then you're not just optimizing for, click-through rate, you're optimizing for other things. So that's one thing that can help. Another thing that can help is trying to understand a little bit more about what people actually want from the recommender system, right? So if it's not seeing stuff that you'll click on, right? If it's user happiness, can we make a better attempt at estimating what that is, right? Estimating actual value. And that requires a number of components that are difficult, but I think some ideas there are being able to account for our sort of myopia and temptation that we have in terms of clicking on things. So the notion that the click is not the reward, but when I click on something, I'm showing you some interest in this, but B, I might not be this perfectly rational individual that only clicks on things that, will be great. And that's what I want to see, because I might be somewhat myopic in my thinking, somewhat tempted by various aspects. And if we can develop models of that, whether they're learned from data or studied via cognitive science and formalized into math, whichever sort of strategy we can come up with, if we can account for that irrationality that people have when they make decisions about what content they consume online, then we can look at their click and say, well, this could be explained by you being perfectly rational and really wanting to see this, but it could also be explained by, you wanting something different, but being sort of tempted by this. And at the very least, then we have this. It's not that the robot knows exactly what you want, but at least it knows that it doesn't know. It knows that, look, I have these two possible explanations for what I'm seeing, and I shouldn't assume that one of them is right, and kind of keep building on that and keep getting that, those brownie points by giving you more and more extreme content. I should sort of hedge my bets between these two things and wait for more information. Or you could potentially do things like ask for more expensive, much rarer feedback, like having a person who spend, at the end of the day, look back and say, okay, well, in hindsight, what would you have wanted to do? And that is much more expensive, but it tells you a lot. It's much more accurate with respect to what people actually want. And so from there, you can maybe start actually combining, learning how to interpret the clicks, not as direct reward, right? But as sort of trying to relate them with what people would say at the end of the day and trying to predict that now will be much better in terms of not just exposing people to clickbait. I
really like that notion of being conservative, the first one, and the second one of getting this kind of bigger picture feedback, which I haven't really experienced myself. I don't know if you've seen it anywhere, but I would imagine what we describe would incarnate as, maybe at the end of the year or once a year, Amazon would say, hey, of all the things you bought in the last 5 years, which ones in hindsight are you still happy you spent your money on? But it seems like you could also go against your business in a case like that. Because if it turns out that you say, well, half the stuff I bought was just impulse buying, I was tempted, and in the moment it felt good, but I really wish I had just saved my money or spent it on something else, then there could be some tension there, it seems, if a company has to choose between
profits and
profit and long-term happiness of somebody who might even spend less time online. If it's Amazon just maybe wants you to buy, but then maybe Facebook wants you online. And so it seems like some of the happiness could come from things that don't then perfectly align with what the companies maybe want.
No, absolutely. And so all I feel I can personally contribute to the world is hopefully somewhat better solutions for estimating that happiness. But I don't know a way to force companies to not just optimize for profits. It's almost, I don't know that much about how companies work, but they're sort of responsible to a board of directors. And it's almost like illegal for them right now in the way things are set up to make decisions that they know are explicitly against. And that's that would be the ask, right? It would be in your objective, you should balance profits that you get from, from the engagement with user happiness. And maybe it's not that you just optimize for user happiness, but you're not just optimizing for profits either. And they'd have to be willing to make that trade-off very consciously and explicitly. And I think right now it's so hard because we don't have great tools for doing the right thing, doing the happiness thing. And because even if you do something, it's just the way organizations work, right? Even if you do something as simple as reporting, profits from this and that team that team contributed to, now all that team is going to do is try to drive that profit up, right? So you kind of have to set their metrics to be, how much have you contributed as a team to user happiness? And that's the only way that they'll try to make the system better and better, work towards that. Otherwise, So it's a political problem, an organizational problem, just as much or perhaps more. I think you're right. Then it is a technical problem. But to the question about are there technical solutions? Not quite yet, but there's some things that we can do that seem to be at least significantly better than the current thing that we assume companies are doing.
Ultimately, seems really beautiful though if you actually succeed and you are able to build a tool that can effectively, with limited interaction, the person doesn't have to spend now all the time with your tool, hopefully, but the tool kind of with limited time from the person can really understand what makes them happy, gives them fulfillment in life and so forth. it seems like once you have a tool that gets somewhat close to that, even if it's not perfect, but is at least getting in that direction, it seems like that would give a lot of leverage onto whoever is putting things in front of people, and you could actually measure. You could say, well, your tool is this much misaligned with actual fulfillment and happiness, just so you know. And I mean, even just measuring it and pointing it out might have a pretty big effect. But it seems we first need your tool that'll that'll measure fulfillment, happiness, and so forth, to make it available. Yeah, which is very much work in progress. Another thing that makes this tool very complicated is that what makes people happy, so our preferences or our values, not only change over time, but what's tricky is that these recommender systems, through the content that they show us, end up influencing them, whether they try to explicitly or not, right? So you have a little bit of this issue that, for instance, by showing me a particular video, by recommending a particular video, you're updating what I believe to be true about the world. And now you've sort of changed what I value, because I just have different beliefs. They could be wrong. You might have updated them in the wrong way or in the correct way, but you've done an update, right? Or by just sort of habit, like you exposed me to a lot of stuff of one type, and then I started liking that because I've seen it, and there's this kind of, recency effect of I like seeing the stuff that I've had interacted with the most recently. And this shift in human values or human preferences, I think, can be pretty concerning, because if you think about the way recommendation systems work, right now, maybe they're fairly myopic. They just try to show you a thing, right, that you'll enjoy. But there's more and more of a shift in the academic community. And so that makes me think probably already in the industry as well, towards longer horizon optimization. So treating it as a reinforcement learning problem. So in other words, it's going to be a sequence of decision that you're making, and you're trying to, have all these recommendations work together longer term in order to do overall, long-term engagement. And that makes sense because we interact with these things repeatedly. It's not one and done. And so what's complicated is that the moment that I set up this system to optimize for long-term kind of cumulative engagement, now I sort of incentivize it to drive the user towards values or preferences that are convenient for it, where it's easier to maintain the user engaged. So for instance, if there's a lot of content of type A and not a lot of content of type B, it'd be very convenient for the recommendation system if the user preferred type A. And so if this fact about, some preferences, some values are easier to satisfy than others, combined with this effect that you can have as the recommendation system on values, you can change them, you can influence them, sort of gives now the recommendation system the incentive and the opportunity to actually purposely change your values over time in order to keep you more engaged, right? And I think that can lead to some undesired effects, right? So when we say make users happy, it's complicated because we can make users happy by making them like, certain things and then giving them a lot of that, but that's maybe not the right definition of happiness. Yeah, because you're saying happiness, there's a higher order thing, is that the way to think of it? There's am I happy today? But then maybe that's fulfillment. I don't know. But there's this notion: was my life a good life? Yeah. Maybe you're happy every day because you're loving the French fries and you're loving the Coke and you're loving the sugar. But then even though you're happy every day, getting big doses of all of that, maybe
don't feel like you've achieved that much at the end of your life. So that's one way that this can go wrong. And I think that it's even perhaps more subtle, and this is very philosophical, but if let's say that people have values and these values change over time, when they look back on their life, they're using the latest value, perhaps, right? Is that what we want to optimize for? Like, is it okay if when they look back on their life, according to their value that they have then, they're satisfied? Is that the objective? Or is it weird that we kind of change the person's values from here to there? Should we be looking at the values according to the sort of the initial value system before we started messing with them, right? So that's I don't have no idea what the answer to that is, but I just wanted to point out that it's tricky. The rec system question is particularly made complicated by the fact that human preferences might change over time as a consequence of the stuff of the interventions that the system itself is making.
Yeah, that part seems really, really hard to even decide what we want. I mean, maybe a person could decide, I guess, for themselves before they've ever been exposed, and then say, I maybe here's the definition of what I want. But even that seems very, very hard. And it seems like deciding on somebody else's behalf seems not a great idea either. I mean, if somebody says they're happy, who are you to question that? Or maybe, some advanced AI systems to then question it and say, well, you're happy for the wrong reasons. That doesn't seem great either. Yeah. Hard problems. Wow. Yeah. Now, when you think about all those things, whether it's, robots that become more capable and then start interacting with humans, or you think about the recommender systems that are already at very large scale interacting with humans every day. How in your mind to extrapolate that? What do you see in the next 5 to 10 years? Where are we as humans going to be interacting with robots and AIs the most, you think?
It's a tough question. I think it seems like it's going to be ubiquitous. It seems like you're going to write in robots, and you might have robot assistants at work, and you might have robots in hospitals. In fact, my dad just went through a surgery, and it was with the Da Vinci robot, which is not really quite automated yet. There was, a surgeon did everything. But you would definitely expect that 20 years from now, we're going to be in a different setup with that. And perhaps we're going to make these medical interventions better. Maybe we're going to be able to provide some decision support for treatments and diagnostics and so on. I think one future that I'm going to talk about, because I think it's basically 20 years plus, but I'm very excited about, has to do more with the sort of neurology and neuroscience side. So there's this one very sci-fi like project that I'm involved in, and it's a collaboration with both UCSF Neurology, Karnesh Ganguly, and with Raj Rao at the University of Washington. And it's on this idea of co-processors. So this is AI used for stimulating electrical stimulation of your brain, not of your brain, but for patients who have had a stroke. So there's part of their brain is damaged and no longer functions in the correct way, even after recovery, right? So they recover some and they get some of their function back. But there's a part that's still damaged and functioning incorrectly, which means that, for instance, as they're trying to do these simple things like reaching for a bottle, right? Their arm and their hand no longer works in the way that they're sort of wishing, like they're commanding it to. And so the idea with the co-processors would be that not only can you take readouts from the brain, as we do with brain-machine interfaces, but you can actually do some amount of electrical stimulation on the brain. And over time, the hope is that you could learn to do this such that this co-processor is, through its actions, it's effectively compensating for the damage that the stroke did. And overall, the person is trying to think about, controlling their arm. And instead of, due to the stroke, their arm sort of going not where they're wanting it to, it just functions in kind of close to the same way as the uninjured brain functions. So it's crazy. It's really cool. But yeah, the idea would be that you start off with something open loop, some very simple policy that maybe helps a little bit, but then over time you're learning from the person actually trying to do this task, or various tasks, how to take actions on the brain, how to provide these stimulations so that you end up with success. There's many interesting questions there, but one thing that really amazed me is that, as sci-fi as this sounds, in Karnish's lab, they've tried this with a very simple system that is not yet doing reinforcement learning or anything complicated, but basically they've looked at injured brains in primates, and right after the stroke, they have a hard time reaching for something and collecting a pellet that they're getting. And they've noticed that what happens in the brain is that normally there's a sort of a sequence of regions that fires in sequence. Mm-hmm. And that sequentiality is kind of broken by the stroke. So they kind of fire, they're now offshoot from each other. And so they figured out a way to stimulate the brain sort of globally, that almost kind of helps reset this clock. So kind of it's a frequency that helps sort of set this kind of, internal brain clock, so to say, that then ends up making these sequences actually fire at the right times. And then when you look at the reach, it's just like a normal, okay, I just go and grab this thing, as opposed to trying and, having a really hard time. And it's amazing. I mean, there's a long way to go, but it's kind of a proof of concept that if you ask me 20 years, I think that there might be things that we could actually do in 20 years on this that are helpful.
That's magical that it can, in some sense, supplement or complement the brain for the missing part. What do you think about, what if there's no missing parts? Our brain is still finite size. I mean, what if we could make it bigger?
Yeah, I mean, I don't know. I'd have to basically think about all the ethical implications downstream, but I am personally very excited about these ideas that enhance human capability, even for people without sort of injuries or without cognitive deficits, that just make us better at being humans. So even without brain stimulation, we like in the lab to work on things where by having a robot collaborate with you on a task. Let's say you're assembling something. Just give a concrete example. It's a little bit boring, but it's concrete. So let's say you're assembling something and you don't know exactly how, where everything is supposed to go and how it works. And actually Brad Hayes did some work in this area as well. So if you have a robot there that actually knows the task, maybe it's not very good at manipulating everything, but it knows kind of the high level, right? What's supposed to happen. Then what it can do is these subtle interventions that kind of nudge you towards doing the task in the correct way. So for instance, they can take something that you might be tempted to grab and use, but that would be the wrong thing, and take it further away from you. Or take something that you're supposed to use and bring it closer, because that, that's and what's cool is that you don't have to kind of program these things in. You just kind of have to tell the robot, here's the task. You have to do this task well with the person. So, and the person if the robot has enough of that model, that understanding of how the person works, including their limitations, then it will figure out the actions it can take such that when the person responds in their sort of, not perfectly rational way to what the robot is doing, they're responding kind of in that as good of a way as possible. Another example is I give you this bottle, and maybe a bottle is not a great example, but I give you this bottle, and the way I give it to you influences the way you're going to grab it. So as a human, it turns out we're not very good at planning ahead. So if I give you a bottle, you're going to grab it in the most comfortable way. And then if you have to put it in a dishwasher, that's why a bottle is a bad example. If it was like a cup or something, I have to put it in the dishwasher, then I have to twist my hand or whatever, or set it down and re-grab it. And so what the robot that knows about how you grasp things and what you're supposed to do with them can do is it can figure out the best way to hand this over to you such that, your sort of comfortable way of grabbing it ends up leading you to just be able to do the task afterwards in the most natural way. So it's like these nudges, this kind of designing what the person is reacting to, the environment the person is reacting to, so that their suboptimal reactions end up actually being optimal, just because the environment is sort of forcing the myopia to be the right decision in the end anyway.
So there's a future then where the robots are effectively the robots are anticipating the things we want and are going to try to do, at least, let's say when assembling furniture or loading a dishwasher. And it's going to be like working with the robots. It's not going to feel like working with a robot. It's going to feel like working with somebody you've worked with forever and who's always looking out for you to make it maximally convenient.
Yeah, and hopefully with someone really, really smart who can kind of like guide you towards, how we do it with babies. Like we don't just let them do stuff. We sort of set up things so that they actually get to succeed at the thing that they're doing.
Yeah,
we be the babies.
The stairs going down, you put a fence in front of it. Because
yeah, I don't know how I feel about that. But another example like this maybe is we were working on this project that we called assistive perception. But it wasn't necessarily for people who have problems with perception. It was also for people who are visually impaired, but it doesn't have to be. The idea is that we're not perfect at doing tasks, right? We're suboptimal, we're human, we're fallible. So we don't figure out the best way to do them. And if you want robots to assist, they sort of override what you're doing, but then you're not doing it yourself. You're not the one actually doing the thing. So it's a different way for a robot to assist. Well, what we started thinking about is, why are you not optimal? And there's many different reasons. But instead of kind of going down the list of 100 different possible cognitive biases that people have, and you're like, well, they react this way and that way and that way, we thought there might be some pretty fundamental reason why people are suboptimal. And that's that perhaps they have the wrong beliefs about the world. That if the robot knows how the world works, the robot knows what's there, what the state of everything is. And so to it, it's very obvious what the optimal thing to do is. But if you're a human and you're trying to estimate where things are and trying to estimate how things work as you act on the world, you might not have perfect estimates of all of this. And that may be why you don't do the correct thing in part. And so one kind of cool assistance thing was, can I, in a sense, modify the observations, what the person sees, so that when it's processed suboptimally by our perception system, which is full of biases, right? It's full of optical illusions are a thing because we have biases in our perceptual system. Like we see things in a different way because our brain kind of has these shortcuts and cheats. Can I kind of show you something else about the world? Maybe like something is, I actually put it closer than it actually is to compensate for the fact that if I just show you where it is, you're going to estimate it as being further. Mm-hmm. Can I sort of kind of lie to you about what the world looks like so that when you try to estimate where everything is and then make a decision of how to act, you actually end up with the right estimate that is as close as possible to the ground truth. And so, I mean, we did this with like piloting this silly kind of landing system, but it turned out that when people pilot an aircraft like this, they're not doing a good job at estimating the tilt. So they seem to be underestimating the tilt. Now, we didn't know this, but here's how we kind of hypothesized that that's what's happening. We had a robot, an AI system that kind of re-renders for them what the scene looks like. And we had it learn to render things in a way that gets the person to estimate the correct thing and then take the correct action. And what it learned to do is it learned to exaggerate the tilt of the craft. And then people, when they saw this exaggerated tilt, didn't take the wrong action, didn't take the action corresponding to the exaggerated tilt. They actually took the action corresponding to the correct tilt. So the robot is kind of saying, okay, well, I know you're going to perceive this in a different way because you're just a human and you estimate things in fallible ways. So let me kind of show it to you such that when you see it, you're going to kind of have the right belief about what it is and then be able to act in the correct way. So that's it's a weird kind of assistance, but it's an assistance where it's again, just kind of trying to compensate for the fact that we're suboptimal and we're still doing all the things, but we're now doing them correctly because we get a little bit of an aid in, how the world works or where stuff is or whatever.
That's so interesting because take that to the next level. We'd all be wearing glasses or electronic contact lenses. Yeah. And it would essentially, it's like an enhance function, but not enhance just making something sharper, but enhance to help us react
modifying where it appears to be or to help us react properly to it. And it's janky because it's lying to people about where stuff is. But the idea is that by showing you these distorted observations, your actual belief, your actual estimate of where, what you think the world looks like is actually more accurate as opposed to less accurate. And if that's the truth, then I'm comfortable with it. The problem is, of course, there's a slippery slope where, you're showing me things that just lead to the correct actions, but don't necessarily lead to the correct beliefs. I have the wrong beliefs. So you have to be careful how you optimize.
Yeah. And how much you still have free will to take the action you want in that sense. Then, if you don't get to see the world very directly, it seems limited use maybe it's ideal. But I could definitely see it in driving, for example. Hopefully, autonomous cars can be better drivers than humans, but it's hard to see if a car doesn't have brake lights. That's why they have brake lights, of course. But if a car in front of you doesn't have brake lights, it takes you a while to notice that they're slowing down. But probably a LiDAR system or even a pure camera system could know much more quickly that car has started to slow down and could probably, somehow change what you see. Maybe projecting artificial brake lights.
It would just put brake lights on
or something. But who knows?
Yeah, or change, the more realistic thing is actually changing the intent. The brake lights don't have to be off, but they have this kind of on or off. But imagine that you actually play with the gradation and the intensity of it in a way that better communicates to people how much you're slowing down. And then maybe that actually helps them react.
Yeah. Some people have their foot on the brake pedal all the time. It seems when you drive behind them, you're constantly like, oh, I should be braking, but actually they're not really braking. So let's quickly check. Is there anything that you feel we should have covered that we didn't cover?
I guess we didn't talk too much about this way to correct for biases. There's this framing, which is if you want to give robots a theory of mind of people and you don't want them to just blindly assume that people are optimal or noisy optimal, there's one thing you can do, which is you can try to enumerate all the list of all 200 biases that we've discovered so far and somehow turn them into math. But that doesn't seem scalable. That seems very, very tricky. And so one thing we've been thinking about is a little bit inspired by the real world. So I found out at some point that in the US, at least, some parents decide to not vaccinate their children for measles. Okay, so this is a decision that parents can do. And I was thinking, okay, well, imagine if I have an AI system observing this and now trying to actually make inferences about what you care about as a parent, right? The AI system actually has access to all of the the scientific data that's out there, chances are it will infer that vaccinating against measles is probably a really good idea for your child, and then it will incorrectly probably infer that if you didn't vaccinate your child against measles, then you must not care enough about your child or something like that, right? And that would be the wrong inference. Now, one explanation is that people are just suboptimal and sort of bad at decisions, and so what can we do is just noise. But in a sense, I don't think it is. I think what happens is maybe those parents have been exposed to specific kinds of articles, maybe because of their recommender systems have sort of shown them that, right? That have informed them that, maybe there's a chance of autism happening if you from the measles vaccine or something like that. Now, perhaps the wide body of evidence contradicts that, but that's not what they saw. Maybe they saw the few articles that are supporting this. And so it would be incorrect to say that people don't care about their kids. It would probably even be incorrect to say people are just kind of randomly noisy. What's actually happening is they're trying to make really good decisions under the objective of actually, wanting their child to be very successful and healthy, but they're operating under the wrong belief about the world, about how the world works and what the effect of the vaccine will be. And so, similarly kind of with robots and having a theory of mind of people, we thought, well, maybe it's not that people are just randomly, arbitrarily suboptimal. Maybe they're actually taking actions that are pretty rational, but under wrong assumptions about how the world works. And that sort of led to this work on assistive perception of trying to correct people's beliefs and work on trying to understand the people's internal physics model of how they think the physics of a system works. And then once you have that estimate, you can sort of translate their actions, which are meant to work with their internal dynamics, which is very simplified, onto the real world that is much more complex and less intuitive. And so we've kind of gotten a lot of mileage out of not just giving up on people and saying, they're so complex and completely unwieldy, and they just like do random things that are completely not optimal, but saying, well, hold on a second. Maybe a lot of what we're seeing as appearance of optimality is explained by these wrong assumptions that they're making. And if we identify the wrong assumptions, then we can do a much better job predicting and understanding their behavior.
That could directly feed back into the recommender system, right? Because essentially you're saying, the information people have been exposed to wasn't very complete. And you infer it from their actions, from seeing what they do. You say it's likely that they've been exposed to this information, but not that information. And let's supplement it to give them the full picture.
Yeah. It's in a way, the assisted perception, but for, how you think about facts in the world, and sort of trying to get people to have the right beliefs about various facts that we think we know in the scientific community, by making sure that by estimating where they currently are and trying to make sure that they get all the nuances and all the facets.
Well, Anca, thank you so much for joining us. I learned so much, even so many new things, even though we talk pretty much every week, yet so many new things I learned today. Thank you.
I am very surprised by that because you know so much about all the work that we do. But thank you so much for having me and taking the time. And I'm really looking forward to hearing this, actually.